Hello and welcome to Electrical Power Conversion. Today's topic is phasor notation. This is Steve. If you have any questions on this material or you wish to reach out to me, please use the email addresses shown. The objectives of this module is to introduce an Euler relationship, illustrate mathematically phasor notation, graphically compare phasors to time domain waveforms, and finally use an example of complex impedance. So first, the Euler relationship. Given an arbitrary function f of t, it's a cosine function, has a magnitude capital F, radian frequency omega, and a phase shift of phi. Euler, as shown on the left, came up with a relationship relating complex exponentials e to the j theta equals cosine of theta plus j sine theta, where theta is omega t plus phi, as used in the arbitrary function above. Writing this in the Euler form, what we have is the real part of the magnitude f times, in the square brackets, the cosine plus j sine term. Now, if we look at that form, if you for a second cover up with your thumb the j sine omega t plus phi term, what you'll see essentially is what we have given above for f of t. The only difference is now we have this real operator outside of that function. The reason we need that real operator is, hold your thumb, now when we bring in that plus j sine term, we have to tell that function just look at the real part, not the imaginary part. So those two forms are equivalent, but the reason we wrote it in that form is now we can capitalize and use this Euler relationship and write it as shown. It's the real part of the magnitude f times e to the j omega t plus phi. And now using a property of exponentials, so for example, if we have e to the a plus b, that can be written as e to the a times e to the b. So that's the identity I'm showing there. And what we'll see in red here is our phasor. So our phasor has a magnitude f and a phase angle of phi. And if you compare that to the function up above, what we'll see is it captures the essence of that cosine function, the magnitude and the phase. What the phasor doesn't capture is the angular rotation omega. So to sum up phasor notation, we're going to use a bold letter, in this case f, with a bar over it to denote phasor notation. That's going to be equal to the magnitude f e to the j phi as shown, or if we want to eliminate the e, we can write it in a more compact notation as just the magnitude and phase. In this course, we're going to use a cosine reference, and that's going to be shown on the next slide. So looking at the magnitude of the phasor, in this course, what we're going to use is the RMS, or root mean squared value. The reason for this is in power engineering or power electronics, that is the more relevant value as opposed to, say, a peak value of a sine wave. A good example on this is if you think about the voltage in your house, it's 120 volts. That's an RMS value of the sine wave. If you actually looked at that sine wave on an oscilloscope, you would find that the peak is roughly 170 volts. So we're going to refer to RMS when we talk about phasors in this course. So the conversion for a sine wave, and we'll assume sine waves unless you hear otherwise, is to convert from the RMS to the peak, you have to multiply by the square root of 2. So with that, there's a note at the bottom of the slide, is phasor notation may utilize either peak or RMS. There's no hard, fast rule that says it always has to be peak or always RMS. Depending on the course, the text, the material that you're looking at, either could apply. So just make sure you understand clearly what you're looking at when you're looking at the phasor relationship. Again, in this course, we're going to focus specifically on RMS. So how do you map between the time domain and the phasor? So coming back to the generic form from a previous slide, the function f of t equals a magnitude and phase of a cosine function. I'm going to give you the specific voltage example. So again, voltage in your house, the RMS would be, say, 120 volts. So if you take 120 times the square root of 2, you get roughly 170 volts peak. Cosine omega, again, using the case for in the US, the frequency would be 60 hertz. So to get omega, you go 2 pi times 60 hertz, roughly 377 radians per second, and then an arbitrary phase shift. Again, if we use a cosine reference as shown here, we're going to define phi as a reference of 0, and we'll see that coming up in a graphic shortly. We can write the time domain voltage notation using Euler's notation as shown below. So the final expression there in this box is the real part, square root of 2 times the bold V with the bar over it. So remember, that is the phasor notation. So that would capture VRMS times e to the j phi. That would be the phasor. And then you have the rotation of that phasor with the e to the j omega t term. So shown graphically, on the top of the graphic you'll see the phasor with a cosine omega t reference and a sine omega t reference. The black arrow would be the cosine reference, and if you were to think of that mapped onto the complex plane, that would be on the positive real axis, and the sine reference would be the red arrow, and that would be mapped on the negative j axis. Now both of these vectors would be rotating at a frequency omega. Note the magnitude here I'm showing as RMS. Below that you'll see the sine and cosine functions as a function of time. Here I rotate the plot 90 degrees. Note also that the magnitude of the sine and cosine functions, the magnitude is square root of 2 times VRMS. So again, talking about the difference between the time domain and the phasor domain, this conversion between RMS and peak, just keep that in mind. So now, as promised, we're going to show you an animation of the time domain and the phasor. First, what you'll see in red is the time domain value. It's a cosine function, amplitude of 1, and then you'll see there's a blue arrow tip with a purple dot at the end on the positive real axis here. Notice the vector length here is roughly 0.7, which is that time domain value, amplitude 1 divided by the square root of 2 is roughly 0.707. Now what I'm going to do is animate this. What you'll see is the time domain value, the cosine wave is traveling through time, and the phasor is rotating. So their phasor is rotating at a frequency omega, which is captured as the cosine wave. And then, so you'll see that rotate. What I'm going to do is actually stop it, reset it here. So again, the phasor as shown, 0 degree reference, you'll have a cosine function. If I go to the plus 90 degrees, notice here the red waveform has a negative sine function. When it's at the 180 degree position, you'll see a negative cosine function. And then finally, this is the sine reference that we took here. So when the phasor is at a minus 90 degree reference, you'll see the sine function. So very useful tool showing some animation characteristics here. And notice if I were to rotate the wave backwards, then the time domain would go in the opposite direction. So we're going to assume a positive rotation going in time as a counterclockwise rotation. Now we're going to show an example of the phasor to time domain mapping. So first we're going to show the phasor graphic. Let's show a voltage and a current waveform. So the voltage, that would be 6 volts RMS at an angle of minus 70 degrees. So the minus 70 would be referenced to the cosine omega t axis. So you'll see the 30 degrees and then the 40 degrees. So adding those to minus 70 degrees as shown here. And the current reference would be 10 amps RMS at a minus 30 degree reference. So to convert that to the time domain, let's first look at the current, I of t. I'm going to say the amplitude is 14.14. Now if I stop there for a second and say, well, wait a minute, I have 10 on the phasor, why do I have 14.14 in the time domain? Well, as a reminder, in the phasor domain we're looking at RMS, in the time domain where it's peak, so you need to multiply by the square root of 2, and when you do that, now you'll see the difference. Now, omega, I don't know what omega is, so I leave that as just a variable. But I do know the phase shift is minus 30 degrees, so I can complete my time domain expression using the cosine reference. However, if you wanted to use the sine reference, you can do that. The amplitude's the same. Frequency, again, omega. now the reference would now be 60 degrees. So if I look at go back to my phasor graphic, if I look at my sine omega t and current with respect to that, I see the 20 degree phase shift and then the 40 to get to the current, so add those two up and that's a 60 degree reference. So similarly for the voltage, you need to do the RMS to peak conversion by multiplying by the square root of 2 and see the phase shifts as appropriate. So some sinusoid phasor relationships. Here's a table that will show the sinusoidal expression on the left and the phasor on the right. The first one we've already seen. The second one, if you multiply the voltage by a factor of k, which could either be a gain or an attenuation, it's a straight multiplication of that amplitude in the phasor domain. If we do voltage addition in the sine time domain, similar voltage addition or subtraction in the phasor domain. And if we do differentiation or integration, I'm going to show a graphic here to explain that a little better. So if I take my original voltage V of t with a 0 degree reference as shown here, my cosine reference, and if I was to take the derivative of that, essentially what that does is, first of all, from a phase shift, it shifts it positive 90 degrees, and also look at the length of the vector magnitude. The magnitude has grown y. Going back to the table, what you'll see when you do a derivative of a cosine omega t term, you have that omega term you have to bring out the front, which will act to make that vector length bigger. Similarly, for the integration, now you'll get a minus 90 degree phase shift, and notice the vector length is a little bit smaller. So when you do the integration of cosine omega t, you have to 1 over omega t division out the front. So an example here for complex impedance using Ohm's law for AC circuit, the complex impedance Z is the relationship is the phasor voltage V divided by the phasor current I. The unit of Z would be in ohms. So here I show a relationship for resistor, inductor, capacitor. Remember from the previous slide, the properties of differentiation or integration come into play here. And so what we'll see sort of the far right of this box is the complex impedance for a resistor. It's just R, it's independent of frequency. The impedance for an inductor, j omega L, and that for a capacitor is 1 over j omega C. So I show this graphically on the right here. The x-axis is the radian frequency omega, and the y-axis would be impedance measured in ohms. So for a resistor, I show roughly a half an ohm. For the inductor, notice the relationship as you increase frequency. So first at 0 frequency, we see that the inductance is 0. So at 0 frequency, we call that DC. The inductance at DC acts as a short circuit. And for a capacitor, you'll notice a generic 1 over x function, and at 0 frequency or DC, the value of the impedance for the capacitor is essentially off the chart, so it's infinity. It's an open circuit. So note at the bottom, the complex impedance Z is truly a complex number and not a phasor, since it does not represent a sinusoid. If the calculation, you have a phasor voltage, a phasor current, the division of those two, you would get a complex number. So that concludes this module on introduction of phasors. If you have any questions, please reach out to me on email at fredette@wisc.edu. Thank you.